it is streaming, and we should be able to see the content in a few seconds. I'm checking on my side. There we go. Alright, so let me close that window because I don't need that anymore. There we go. So, this is the ungraded assignment, quote unquote. So it's not really an assignment, it is really just a suggested activity for people who want to kind of maintain their knowledge about what we have done so far to kind of implement this code. Now this code is kind of interesting in many ways. I have already posted a few questions down here. Okay, so this is how you don't have to be able, you don't have to complete it. Okay, this is really kind of more or less a thought exercise for people to kind of keep thinking about these things, and the more you think about it, the more likely that you can absorb the solution when I talk about it today. In other words, I'm not doing this for myself. I mean, obviously this is actually more work for me, but I would like to think that this might help you understand the material a little bit better. And you absolutely do not have to agree with me. Every person is entitled to his or her or their opinions. So we're gonna start with this, and then we'll talk about a few additional examples, and then we'll go into today's lab is going to be easy peasy because it only has like 3 easy questions, but that's only the first part of what you need to do. So the second part is to actually finish a program that you have to turn in a week. So I would suggest people to pace yourselves, just so that you do not find yourself running out of time to get it done. Okay, so we got some text messages in Discord, and I think a good portion of the class has joined in already. Alright, so when we return a value, we know we have to put it in register A, but how do we determine the scope of a return parameter? I'm not sure what you're referring to as a returned parameter. And then the next one says, I am curious to see how different your solution is compared to mine. Sure, yeah. I mean, looking at differences is a form of critical thinking. I'm not sure whether I have told this class or not. I'm writing something about critical thinking and also abstract thinking. So far I'm still working on just the critical thinking part. If you guys are curious, I'm more than happy to release whatever I have. Okay, so this is titled Abstract and Critical Thinking, and I have finished only a small portion of that because I have to do this during only my spare time. But it's something that may be of interest to some of you. Anyhow, curious of how I handle x is less than y and a returned value. Okay, so okay. So the return value is only at the interface right between the end of the callee and the continuation of the caller. So right at that moment, right at that transition, register A is guaranteed or should be guaranteed to contain the return value from the callee. And then after that, it is entirely up to the caller to do or not to do anything about the value in register A. So yes, so a lot of that. So the callee just has the responsibility of putting the return value into register A, but the caller can completely decide and say, I don't need the return value, and just completely ignore the value in register A. Okay. So it's a 1-line guarantee, but when register A will still have the return value, depends after that. Right, so it's entirely up to the caller to decide whether to use it or not, but it is the responsibility of the callee to make sure that the return value is in register A when it returns control back to the caller. Alright, so let's go ahead and get started, okay, because today is going to be pretty full because I got quite a few examples to go through. Alright, so what we see here is a sample program. You can look at the right hand side or the left hand side, doesn't really matter because they're kind of the same with syntax highlighting on both sides. So if we look at this code here, that's exactly the same code that I gave you guys last Tuesday. And we're going to implement it today. And there are a few things that you might want to pay attention to as we work on this code. So all of these are the questions, regarding what you might want to pay attention to. So you have to pay attention to the local variables. So main has got 3 local variables, I, J, and K. So we want to understand how we allocate the local variables and parameters on the stack, and who is responsible to allocate what. Okay, so that's one thing. We certainly have calling and returning, and at this point, calling and returning really should not be a big issue, and we only got one place where there's a call, which is right here. How to specify return value, which we were just talking about it in the text channel. It is through register A. And in this case, the return value is an integer, but at the same time, the expression that we are returning is, if you look into this expression here, it is x is less than y. So x is less than y is quote unquote supposed to be a Boolean, but it can also be interpreted as an integer, because in C and C++, the value 0, the integer value 0 can be considered as false, and any other value, any other integer value is considered as true. So that means if x is indeed less than y, we can return a value of 1, we can return a value of 2, we can return a value of 255, 254, 128. It doesn't matter as long as it is non-zero. It is actually just saying, yeah, it is true. So that part is, I guess, that part depends a little bit on how well you understand Booleans relate to integers in C and C++. Now, C++ does have a bool type, B-O-O-L, bool type, but at the same time, if you try to do something like this, it is completely legitimate in C++ as well, because the ability to cast a Boolean back into an integer is built into C++. It's part of the language specification. Now, something like that will not work in Java. So the Java compiler would actually scream at you and say, hey, x is less than y is a Boolean, but the return type of this function is supposed to be an integer, and the compiler would just stop. It will give you an error instead of a warning. A C++ compiler, on the other hand, would just look at this and go like, yeah, we know how to do this, no problem. So there is that. Let me just kind of go through the list a little bit more. So we need to talk about comparison, signed versus unsigned comparison. That we talked about a long time ago when we talked about signed versus unsigned representations of integers. So I hope you guys do vaguely remember the flags related to the subtraction. After subtraction, we have the borrow flag, which is now known as the C or carry flag, because they are kind of merged into one. We have the Z flag, we have the O flag, we have the signed S flag, and we have the L flag. So we have to choose the right one in order for this code to work correctly or to be consistent with the C code. And then we have a conditional statement, which is the if then else statement. And that part, has to do with the translation of the code. We first have to kind of flatten it, and once we flatten it, then we kind of have to decide, okay, now what do we do about this code? So let's get started. So let's see, what am I going to do is I will put this code into an editor first, so that way I can do all the editing in my favorite editor. And let me see, where's my there we go. Alright, so we're gonna start with just translating the main C code, just the frame itself, into, in other words, we're flattening the structure code so that it's no longer structured. Okay, so we're gonna deal with that first. So we'll see. Let me see how I should do this. Alright, so I'll put the program into the temp folder and we'll call that less than. Okay, that's not very inventive, but we'll go with that. So cat to lt.c. So we'll start with the C program first. And here is my paste, and there we go. Alright, so this is the original C code, and the first thing we're going to do is to apply the flattening technique, okay, that we have already talked about I think last Tuesday we talked about that, which is basically just turning something like this. Okay, let me turn on line numbers. Oops. So it is basically turning line 10 all the way to line 17 into something that is flat, okay, that does not use braces. And some people can argue and go like, but braces are not really needed in this case because I only got one statement to talk about. But the braces are here to suggest that we have a structure. So we want to kind of remove that structure here. So if you remember that discussion, the first thing we do is we negate the condition that we are checking. And then we get rid of the braces. So this is removed. And then this one has a go to. And we want to go to wherever the else branch is supposed to be. So I'm going to use else branch as the name of the label. And then this else is also going to be gone, because if you are flattening the structure of a conditional statement, there cannot be an else in it anymore. So the else keyword is gone. It is replaced by the label else branch. In other words, I'm using much more primitive constructs in C and C++ to implement the same control structure. Now, after k equals 1, we need a unconditional branch, which is a go-to the end of the if statement, because otherwise it's going to continue with k equals 1 on line 14 at this point. So I have to get to the end of the conditional statement. So I'm going to say, and label. And the end label is going to be located here because this is the actual end of the entire conditional statement. Alright, so this code is going to function exactly the same way as the other program, except this one does not, it's no longer using structured code. Do we have any questions about what I just did with this code here? Okay. Alright. Anyone else? Because as I have mentioned many times already, if you do not want to ask a question in the text channel of the class, you can always DM me and I will, answer those questions. Oh, here we go. I forgot a semicolon here. I have been doing a lot of Node.js programming over the weekend, so I have not been using semicolons. There we go. Alright, so this is the code that is going to be about the same as the other one. Oh, okay, so Perry is typing something. And there's no need to take row anymore. Okay, well, I'm going to continue here until I see the text. Alright, maybe not. Yeah, you guys can also use the voice channel if you wish. I think Matt might be putting the emoticon onto in the wrong channel. So it seems, okay, because there's no context for that. Alright. Yes, what I'm doing is slowly converting the code into TTP ASM. Oh, the pause? Yeah, that's kind of okay. The long pause. Alright. So the answer is yes. I am converting the code. I'm doing the human compiler thing. Okay. So the next thing we want to do is to get rid of this negation. Well, but this negation can be easily done with just comparing with 0. So we are basically comparing that to 0 because that means exactly the same thing. Okay. If it is because what the negation is trying to do is to see if f of ij is false. So if I compare to 0, it also confirms whether it is false or not. Because remember, 0 is false. in C and C++. Okay, so that's our ticket here. All right, so I think I have done everything I can with this code before we convert it into assembly code. So now it is going to start with the assembly code. All right, so let's go ahead and just change lt.c to lt.ttpasm, and the first thing we're going to do is to comment every single line because, well, I mean the branches can continue as they are because the syntax of defining a label is the same, but I'm going to change everything to comment. So 2 slashes and a space. There we go. All right. This is why I like Vim, because it has regular expressions. There are a lot of cool things you can do with regular expressions. All right. So the first thing we're going to do is the usual no op because I intend to run this in the simulator, and then we JMPI to main because otherwise it will start with the function f, which is not what we want to do. So here's main, and here is f. There we go. And okay, which one do you guys want me to start with? Do you want me to start with f, or do you want me to start with main? If nobody has any, oh, okay. Yeah, if no one has any preferences, I was about to start with f anyway. It's just the correct order. All right, so now this is just what I do is, I would look into the parameters and I want to kind of visualize what is going to be on the stack in what order. So I always put the item at the highest address first, because this way it looks like it is higher. And then the second one is over here, and then this is where we can find the return address. And that is what we can expect on the stack at the entry point of the subroutine. Now, with only 2 parameters and we don't have any local variables, it's probably okay not to use the label approach, but I want to be consistent. So I'm going to use the label approach so that y is 2 bytes away from where d is pointing to, and then x is only 1 byte away from where d is pointing to. But at this point, I'm going to use a prefix. So, if it belongs to function f, I'm going to use f underscore to clearly indicate that these are names within the function f. Okay, because otherwise, if main has kind of the same local variables, then we kind of have to, it'll be confusing. So I don't want that confusion. All right, so now we can implement the return statement. Now, as I have mentioned last week, the return statement has 2 components. Okay, even though it looks like one single statement in C++ or C, it is actually consisting of 2 distinct phases in assembly language. The first one is to figure out the return value, and then the second one is to actual return control or continue execution at the caller. So we'll handle those 2 one at a time. So we'll handle the comparison first. So with this comparison, we need to get to the values of the parameters. Okay, so I'm going to use LDI. The register I'm using here doesn't really matter. Okay, I'm going to use register A, and this is X. So at this point, register A has an offset from where the stack pointer points to get to parameter X. And then at this point, it has the actual address of X, which is close to what we want, but not quite exactly what we want, because we want the value of X. So we can do a LD AA. So now register A does have the value of parameter X, and then we're going to do the same thing with Y, but using a different register. BD, LD, BB over here. So now at this point we have X in register A, and then we have Y in register B. Oh, right, yeah. The assembler would complain and say, hey, this label is not defined, but Jonathan is correct. I forgot to use the prefix for all of this stuff here. There we go. Thank you. All right, so now we can actually perform the comparison. The comparison is trying to confirm that X is less than Y, and we don't really have a choice here because we only have the confirmation of whether the minuend is less than the subtrahend. So we don't really have an option in terms of the conditional branch. But before we get to the conditional branch, we need to compare. Now, in this particular case, you can use a compare or you can use a subtract, because when we're subtracting, we're only affecting the registers containing the values of the parameters. So nothing is really happening to the parameters. So either way is actually okay. But I'm going to use compare because that would be the right opcode to use. And we want to compare A, B like this so that we can confirm whether A is indeed less than B or not. Now, if you compare it the other way, it kind of works too, but then you have to also look for equal to, because when A and B are the same, you want to return false. So there are at least two ways to do this. Okay, so whichever way you want to do it is fine as long as it gives you the right answer. So in this case, I am subtracting A from B, which means I can confirm whether A is less than B or not using a single conditional branch. So now the question is, which conditional branch should I use? There are 5 that we can consider. JCI, JZI, JSI, JOI, and then JLI. Which one should I use? Richard is probably trying to type the answer, so I'm going to wait. JLI is correct. Okay, so JLI is the correct one because JLI, the L flag, is the exclusive or between the sign and the overflow flag, and it is a 1 if and only if the minuend is less than the subtrahend interpreted signed. So if you want to kind of review that we talked about many weeks ago. Okay. JCI is useful for unsigned comparison. JOI is very seldom used. Okay, the only time I can imagine that you would use JOI is when you need to detect whether a signed value is out of range or not. Because after an add or subtract, if the value is out of range, then the O flag would be a 1. The thing about C and C++ is the language itself does not check for moving out of a range, a value is out of range. So that's why we don't really use JOI a lot when we're just translating C or C++ code. Yes, those mnemonics are very specific to the TTP. Typically, when you're using a different processor, it would still be kind of like JZ would be jump if 0, JC would be jump if carry or borrow. So it will be very similar. It will start with a J and then start with another flag. The L flag is unique to the TTP ASM. The Intel architecture probably has a different word to describe basically the same thing. The Intel architecture also has the negated branches. So in addition to JLI, it would have something like J and LI, which is not less than. So it has basically a whole bunch more conditional branch instructions compared to the TTP ASM. And then the other difference between the x86 assembly language and the TTP ASM language is they would, in the x86 assembly language, it would use the same JMP instruction. So if you have a label to go to, it is just going to be the label. But if you want to use a register, which is our JMP, not the JMPI, it would put kind of like a bracket or parentheses around the register. Or the register has to start with a % symbol or something like that. So it's a different syntax. The TTP-ASM is as simple as it gets. Okay, when you compare it to the x86 assembly language, which is actually a whole lot harder to understand compared to what we are dealing with here, because there are tons of, I think there are like 8 addressing modes, and each one is slightly different from the other, and some are syntactically very close, but it actually means something that's entirely different. So there you go. Anyhow, so now we have a JLI, and the JLI is to confirm that it is less than, which means we should return a 1. So I'm going to invent a label here, which is f return 1, and immediately I would go to that place, put in the label definition, and then also comment and say return a value of 1. Alright, so what if we do not perform the branch? What does it mean? Well, if we do not perform the branch, then we know that x is not less than y, which means x is less than y is false, which means we should return the value of 0. So we can now do a LDI a with 0. And over here, we are supposed to return the value of 1, which is LDI a with a 1. Now, the problem is, if this is the code that I have, then LDI A0 is going to fall through to LDI A1, which means, it's going to return a value of 1 in both cases, which is not what we want. Okay, so we need to jump around the returning of 1 code. So we have to go to f return, which is just a point where we continue execution at the caller. So now at this point, we just want to specify the code at the end of a subroutine to return control to the caller. So let's see, we will do a LD. Cannot use register A because register A now has a purpose of being the return value. So we're going to use register B. So this will get the return address into register B. Increment D, this is deallocating the return address. And then JMPB is going to continue execution. It's basically just copying the value of register B into the program counter, and that's how we continue execution at the caller. Alrighty. Now we can start with main. Alright, so main starts with the initialization of the stack pointer, and we also want to have, why doesn't f return 1 needs to jump anywhere? Because it falls through to where we want it to go. So after we put a 1 into register A, it would just naturally fall through to f_ret, which is the code that we need in order to return to the caller. And that would be the right place because we just need to specify a value as the return value, and then we are ready to go back to the caller. So it doesn't need a particular branch. Now, if you want to, this is not wrong, but it is also entirely unnecessary because this JMPI really does not serve a function, because without the JMPI on this line, it would have kind of fallen through to fret anyway and continue to return to the caller. So that's why f_ret1 does not need to branch anywhere because it can fall through to where it needs to go. Alright, so getting back to main. Now we also need a picture of what the stack is supposed to look like from the perspective of main. Now main is not being called, okay, unlike in the case of C and C++. Main here is not really a function, but it is merely just a starting point of the entire program. But it still has its own local variables, and those still need to live on the stack. So depending on how you want to do it, I would allocate I first, and then J, and then K. So the allocation is sequential in the same order that I encounter the declaration of the local variables. So that means this is at the offset of 2, offset of 1, and this is where the stack pointer should point to when we have the stack set up. So we'll start with labels. Okay, I is going to be 2, J is going to be 1, and yes, I forgot about the prefix of main. So this way we don't have a problem with different subroutines using the same name as its local variables or parameters. And this is K, and that's going to be 0. There we go. But the label definitions does not actually do anything with the stack pointer. So in order to allocate these 3 local variables, now we need to subtract 3 from the stack pointer. You can do decrement D 3 times, or you can load a value into register and then subtract that register from register D. That will work as well. Now someone's going to say, but Tech, can't you just kind of combine all of this stuff here with subtract DD and just load 0 minus 3 into register D? The answer is yes, I could have done that, but I did not do it because this is the initialization of the stack pointer. this is how we do the allocation. I do not want to combine those two into one single operation because logically they are two separate things that we need to do. Alrighty. When I initialize a number, it starts as 0. I'm not sure what you're referring to. What do you mean by initializing a number? You mean the register or content in RAM? Okay. Oh, in register C? In register C. Oh, in C code. Well, C code does not have any initialization. It just allocates. This is all we are doing. We are just allocating some bytes on the stack. They remain uninitialized. No, that is not the case. So okay, so back to the C code here. This is just allocating space for I, j, and k, and the values of I, j, and k as uninitialized local variables can be anything, because the stack can have some leftover content from prior execution of the program, so we don't know what values are going to be in local variables I, j, and k, and that's why they kind of need to be initialized before we use them. Alrighty, so now we are ready to actually do some work over here. I is getting a value of 2, so LDI A2, this is the right hand side. Now we need to work out the left hand side. So we cannot use register A anymore because register A is our right hand side. We're going to use register B, and this is the offset, this is the address, and once we have the address we can store. There we go. So that's how we initialize, that's how we perform this line over here. I gets a value of 2, and we want -1, kind of the same deal. Register A is now -1. The TTPSM assembler will automatically figure out the bit pattern of -1 is FF, so that's kind of automatic. And A isn't using the label. I'm not sure what Matt is referring to. Are we referring to register A? Okay, alright. Alright, so now we have, what is the, oh, J, that's right. So main J is the offset. Now we have the address. Once we have the address, we can store to the address, which is where the local variable is located. And now we have something that is kind of awkward here. Okay, so let's focus on, let's focus on line 62 over here. All right, so if you think about it, okay, what should we do first? Okay, do we want to deal with the conditional branch, or do we want to deal with the function call, or do we want to deal with the comparison? Which one has to come first? Well, we cannot do the conditional branch without knowing what the condition is. So in order to find out what the condition is, we have to perform the comparison. But we cannot perform the comparison until we know what the left-hand side of the comparison is. So we have to perform the function call first. So you guys are all correct. We need to perform the function call first. So this is how we translate the code. You have to logically think through a statement in C. No matter how complex it looks like, you have to think about it and then figure out the dependency between the various constructs on that line. Because you have taken CISP310, you understand the meaning of a statement already, and that means you should be able to figure out the dependency of, okay, I need to first do this, and then I need to do this, and then I need to do that on the same line. Alright, so we're going to have to deal with the function call first. So to do the function call, what do we need to do first? In this case, f has 2 arguments. So what do? We need to push the 2 arguments first, right? So Jonathan is correct, as part of the operation to push j and then I on the stack, we have to decrement d. So you can do it in a few different ways. All right, so over here, I could have used different registers here so that I can retain the value of the local variables, but I didn't do it because I want to make this code as kind of verbose as possible. In other words, I'm not doing any type of optimization so that it is kind of really spelled out, how to perform, how to translate each construct into TTP ASM. So the first thing we need to do is to push J. Okay, so we are going to do LDI A with main J, add AD. So now A is the address of J, and then LDAA. So now we have the value of J, and now we need to push it on the stack, which is a decrement D STDA. Now we have J pushed on the stack. Okay, so you go like, next we need to push I on the stack. Easy peasy, just copy, paste, and then change J to I. Let's try that. Okay, so we're gonna say 62 to 66, copy to 67. There we go. And then we just have to change J to I, and we're done. Well, I can tell you that this code is not gonna work, because at this point, right at this point here, okay, the stack doesn't quite look like what we think it is. Okay, let's think about what the stack looks like at this point. Okay, we still have I, we still have J, and we still have K. But now we have one additional item, which is the value of J being pushed. So the stack pointer is actually pointing here because this J here is the argument that we are trying to push so that we can call function f. The return address is not here yet. Okay, so when we need to compute the location of I, it is no longer just 2 bytes away from where the stack pointer points to. It is now 3 bytes away from where the stack pointer points to, meaning that I need to do something like this. So the 1 plus is here to adjust for the extra item that we just pushed on the stack. In other words, the stack does not just have I, J, and K in it anymore. It has I, J, and K, and I really should call this argument. I'm debating whether to use argument 0 or 1 because we typically want to count from 0. I'll just say argument 1 of calling f. It is actually on the stack right now, so that means the distance from where the stack pointer points to the various items, like the local variables, is now they're all off by 1. We need to account for that off by 1 by using a 1 plus here. It's not plus 1 because it is a suffix notation, is a reverse Polish notation. So we specify the values and then we specify what to do with the values. So this is important. Okay, this is really important. So now we the rest is okay. The rest is actually correct. Okay, because we just have to, when we compute the offset, we have to make sure that we account for that 1 extra byte on the stack. All right, so now that we have pushed J and I on the stack, it is time to actually call the subroutine. So to call the subroutine, we have to first push the return address. So we can do it a few times in the different ways. So we have a .6 plus in this case, decrement D, STDA. So now we have the return address pushed, which means the very last thing we need to do is a JMPI to the entry point of the subroutine. So we just JMPI to F. And so at this point, we have the execution being passed to the subroutine. And when the subroutine returns, we want to perform the additional operations. Yes, so Jonathan is correct because main I as a label is no longer the correct offset to local variable I on the stack because we got the extra item, which is argument 1, the second argument I should say. Okay, that's my mistake here. Because the second argument of calling f is already on the stack, so the stack pointer is no longer pointing to K anymore, and as a result, the offsets are all off by 1. Is that okay? Actually, there we go. Okay. All right. So if you are working on this program, okay, and you say, okay, we have written a lot of code already, okay, so what are we going to do? Well, you might want to just kind of put a halt instruction at the entry point of f, which is all the way up here, okay, up, some more, there we go. All right, so you might want to put a halt instruction here, okay, which basically stops the execution of the entire program. But when if you put a halt instruction here, you can actually run this code in Logisim in GUI mode, and you will still be able to see the content on the stack, because now we have pushed everything on the stack, but we haven't really started to pop anything from the stack. So this will allow you to verify whether parameter y is in fact local variable j, and then parameter x is really local variable I of main. So it gives you a chance to double check things before you make the assumption and go like, yeah, I think that's working okay. But if you push the wrong values on the stack, then function f is not going to work correctly. It's not going to return the right value and so on. So that's why, when you're writing the code for today's assignment, you probably want to do it in stages and be able to test the program, step by step in stages as well. Of course, that is just a suggestion. Okay, I know some people are just going to ignore that entirely and go like, well, Tech, you only need to do this because you're a poor programmer. I'm a much better programmer. I don't need to do stuff like that. I can just write the entire code and it's going to work the first time. Well, that's fine too. I certainly cannot do that. All right, so getting back to where we were. All right. It depends. I think some people may want to project a more competent self-image, when they're in an interview. But guess what? The interviewers probably know that most people cannot really write programs in one go and actually get it to work. So yeah, understanding the process is correct, is good in an interview. All right, so when f returns, we're going to get back to this location here. And what do we need to do after f returns? Is there anything to clean up? I'm just going to ask that question. What is on the stack right now, right after f returns? So if I were to put a no op instruction here, okay, so when I am at the no op instruction, what is on the stack? Yes, so the arguments are still on the stack. So we kind of need to clean it up. So we just need 2 increment d, one to clean up the first one to clean up after the first argument, the second one to clean up after the second argument. And we don't really care about the values of the arguments on the stack because those are only intended for the subroutine to use. The caller doesn't really need it back, so we are just incrementing the stack pointer to deallocate those items from the stack. The return address is gone already. The return address is taken care of by the callee. Okay, the subroutine being called is the one responsible to deallocate the return address. That's part of the agreement between the caller and the callee. All right, so now finally we got everything cleaned up. The return value is in register A, and what we need to do is to compare that to 0 because that's what the C code is saying. But we already know there's a trick to check whether a register is 0 or not. And what is that trick? We just need to get the register through the ALU, right? Exactly. So AND AA will do the trick. So AND AA is going to force the value of register A through the ALU and affecting at least it will affect the Z flag and also the S flag. Both flags will be changed according to the value of register A. We only care about the Z flag because we just want to know whether it is 0 or not. So a JCI is going to be able to help us with something here. Yes, so it is a bitwise AND. which means the value of register A does not change because of the AND operation. We're only using this to kind of force the content of register A through the ALU so that we can check whether it is 0 or not. It's a shortcut to do it. Yes. So whatever the value of register A is going to be preserved by the AND AA operation, because if you AND a bit pattern with itself, the end result is the original bit pattern. It would not change. No, that's fine. You can use another register, hold a 0, and then do a compare. That works too. I'm just, yeah, I guess I'm using a little shortcut here, but it's not based on reusing registers from previous. So I guess it's okay. All right, so JZI. The question is, JZI to where? Well, if you read the original code says if the return value of f, of calling f is 0, go to else branch. Oh, okay. So that's what we're going to do. Go to the else branch. And we need to uncomment the label else branch just so that now we have the correct label definition. And that's it. Okay, so now we are done with line 85. So everything from, I'm just looking at the code. So everything from line 61 all the way to line 84 is implementing what line 85, the C code on line 85 is trying to do. So as usual, I'm not putting a lot of comments into my own code because I want you to do it. Okay, so remember the format that I suggested using a spreadsheet. You have multiple columns, one column for the actual TTP ASM, one column for you to track what is supposed to be on the stack if the stack content has changed, and then one column for register A, one column for register B, one column for register C. Register D is kind of debatable because it is already reflected by the content on the stack, so you can actually denote what the stack pointer should be pointing to when you're showing what the stack should have at that point. So register D may or may not need its own column. That part is up to you. Alright, so now we can move on and implement k equals to 0. So that one is pretty easy. The stack is balanced at this point, so accessing k is really the usual thing that we do, which is loading the label into register A, add AD, and oh, I forgot about the 0. Well, let's see. Yeah, we kind of need to deal with the 0. Put a 0 into register B, and now we can say STAB. So that would put a 0 into local variable k, and now we can continue execution at end label. And every goto is really just a JMPI, so we just go to end label, and then make sure that we uncomment end label as a label definition. So now we are down to one single thing. Well, not exactly one, but we're down to the last assignment statement. And that one can be exactly the same as these 4, except we are putting a 1 into local variable k. So copy 4 lines, and then change the 0 to a 1. There we go. And now we are almost done. And some people are going to say, but you're done, Tech. No, we are not done yet. Okay, and can someone tell me why we are not done yet? What is on the stack? Yep, we have to. The stack pointer is not 0. That is correct, and then Terrence is also correct. Because what Terrence is saying is how to correct the problem. We have to deallocate. What are we deallocating, and how are we going to do that? Yep, we still have I, J, and K on the stack. They are not supposed to be in use anymore because we are now at the end of main. So we just have to do an increment D, and increment D, so that now the stack is now balanced, which means there's no item on the stack anymore, which is appropriate for the ending of this code, and then we'll put a halt instruction here so that the program would actually stop at this point. All right, so and I can type all this code here all day long and try to explain how this is correct, but we don't know whether it's correct or not, right? So we'll go ahead and check it out. Now, before we check it out, what do you think is going to be the value of k? Should the value of k be 0 or 1 when we run this code? It should be a 0 because I is 2, j is -1, and in the subroutine f, we are just checking whether parameter x is less than parameter y. If it is the case, no, Jonathan, you're incorrect. I was 2. K is supposed to be 1. Because when f returns true, k gets a value of 0. When f returns false, then k gets a value of 1. Yeah, so I kind of inverted that. Okay, so in this case, k is supposed to be what? F is supposed to return false, and we go to the else branch. K should get a value of 1 in this case. Okay, now there's no point in testing a program if the person who's testing the program does not know what the program is supposed to do. There's no comparison that can be done. So that's why, when you are testing your code, you need to understand what you should expect to see before you test the code, and then you can compare what you are expecting versus what the program is actually doing, because otherwise there's no you cannot compare the outcome of executing a program with the intended outcome of the program. Alright, so we are done here, and we can now test the code. And obviously I'm going to take the super shortcut of using my script here. lt.ttpasm. Alright, so it's all done. And now I need to go find my assembler, which is right here. Nice. You guys can go here too if you want to, just because you can just take a snapshot. Okay, I'm putting it in the text channel again, just so that you guys can click on it and be there like right away. Alright, cool. So what are we checking? We are checking to make sure that local variable k has a value of 1. Okay, and we also want to make sure that the stack pointer is balanced, which means it is 0 at the very end. Alright, so we're going to scroll to the end, and we can see the stack pointer is indeed 0, 0. Kind of cool. And we can also see that location FD is getting a value of 0, 1. The question is that really local variable k of main? What do you think? Well, let's see. The first one we allocate for is I, which is at location FF. The second one that we allocate for is J, which is at location FE. And then the third one that we allocated for is K, which is at location FD. So indeed, we put a correct value into local variable k of main, which is 1. Alright, so there you have it. Are there any questions about this particular program or the process to get this program compiled into TTP-ASM? Alright, why is k at FD? I think I just mentioned it. Because FF is I, FE is J, and then FD is K. We did the allocation in that specific order. It is also consistent with the comment of the code. Now, how you want to allocate your local variables, there's no specific right or wrong way to do it. Okay, unlike parameters. Okay, because parameters, there's always a right and a wrong way. There's always a right way, and then the other ways are wrong. That's because with parameters, it is an agreement between the caller and the callee. With local variables, as long as the local variable is used consistently within the subroutine, There's no wrong way or right way in terms of the ordering between I, j, and k. So right here we can see how I is at an offset of 2 and the offset j is at an offset of 1 and k is at an offset of 0 from where the stack pointer points to. But the stack pointer is adjusted, it's decremented 3 times. So the first time it is FF, the second time it is FE, the third time it is FD. So that means K is at location FD in this case. Alright, and then Matty said, could it have been done without using the JXI mnemonic? And the answer is no, you cannot do it without the JXI mnemonic. Because that's the only mechanism that we have to perform conditionals, to perform anything that is conditional. Everything else is not conditional. So whenever you need to make a decision and then based on the outcome of something, sometimes you want to go this way, sometimes you want to go the other way, you have to rely on some kind of a JXI instruction to do that. The question is, which flag are you going to use, right? Because if you're checking whether something is 0 or not, JZI would be the correct one. If you want to check if the minuend is less than the subtrahend, then you have to choose between JCI and JLI. JSI is useful if you just want to check whether the most significant bit is a 1 or not. And then JOI, as I said a little bit earlier, is really useful if the language wants to make sure that the result of an addition or subtraction is within range. But since C and C++ does not have that feature, JOI is seldom useful on its own. All right. So I'm still waiting for Maddie's text to come up. And let's see, I'm going to go back to Joplin because it's actually helping me to keep track of what I need to go over in the class. Quite helpful, actually. All right. When is the final exam? There you go. Yep, just have your own notebook, and jot down the time marks, because that will allow you to go back to a particular section of the recording without having to watch everything from the beginning. So that's a good idea. That's a good idea. All right. So to answer Lisa's question, let's go ahead and check. So I am just searching for American River College final exam schedule because this is a fully synchronous class, so we actually have a designated time for our final exam, just like a face-to-face class. All right. Yep, I have clicked this many times already. Do not try to help me. I do not need help. Go away. All right, so this is a daytime class, right? Because if you look outside, it does look like daytime to me. And the class starts at 9 a.m. So we are a Tuesday, Thursday class. So this would be our day of final exam. It would be December 14th on the Tuesday from 8 a.m. to 10 a.m. You are on the wrong row. Oh, am I? Tuesday, Thursday. What? I think I'm on the right row. Because the lecture start time is between 8:15 and 9:25 because we start at 9 a.m. So, and the class is a Tuesday, Thursday class. Okay. Okay. Because I thought that I was wrong. I mean, it wouldn't be the first time that I am actually wrong, but it did not seem that way, and that's why I was a little troubled. I don't have a problem being wrong. Okay, I'm pasting it into today's text channel, just so that people have a reference to this. And I'll even paste the URL to this page, so this way people can actually go back to the page to check if they want to. There you go. Oh, that's funny. William said, I didn't even know those schedules were a thing, to be quite honest. This is the schedule that we use for fully face-to-face classes, but it's also used for synchronous classes, fully synchronous classes, which this one is. And I intend to get back on campus by fall 2022. So if you are still going to be around, you might be able to find me in my office in fall 2022. I might actually go back to the office to do certain things in spring 2022, but I don't have any classes in spring that is face-to-face. All right, cool, excellent. Now we get back to Joplin so I can remind myself what I am supposed to talk about next. And I need to check the time. It is, okay, we still got a little bit of time. All right, okay, this is important. Okay, so this is the next program we're going to do is we have a very simple subroutine that returns a value of 5, another really simple subroutine to return a value of 7. And then we have a third subroutine to call each one of these two subroutines and just return the sum of the return values of these two subroutines. This looks simple, okay, but it is actually a little bit more tricky than it seems, okay. And to just so that you have another reference to this kind of code, the previous assignment, let me go back to way too many tabs. Okay, let me see if I can find it. Return calling and returning from subroutine. Nope. It's the one that has to do with return values. Nope, I cannot see it here. Oh, darn it. Okay, so let's look for 310. And of course it has to be on a different tab. Alright, so I'm gonna stick it here. Alright, so there's one assignment that we did earlier that actually has a sample code that's exactly what I'm trying to illustrate here. That would be the one up here. I'm gonna copy the link and put it into the text channel because you might want to refer to it to do your current assignment. Okay, I'm gonna put it. So the link is already in the text channel. All right. It's question number 1, by the way. Question number 1 of the lab that I just linked to from the text channel is something that you might want to review because it is actually illustrating a concept that you need to understand for this particular lab. That's the program that is due next Tuesday. But getting back to Joplin, we're doing something like this. So the question is, how do we implement something like that? Okay, now this one does not even have conditional stuff. Okay, there's no control statement, there's no if then else, there's no loop, and so on. It really is just about calling subroutines, handling the return values, and being able to use the return value of subroutine that you're calling in order to compute your own return value. Main doesn't even have a main because I think dirty is going to be able to illustrate what I need to illustrate. So there's no actual main in this case. Now, if you want to test the code, we can just go ahead and call dirty, in main. I mean, we can certainly do that. All right, so let's go ahead and take a look at this code here. And let's see, where's my... There we go. All right, so let's do this. And we're going to call this dirty. In case anyone is trying to figure out why these subroutines are called the way they are called, it has to do with the value they are returning. So I'm going to make a main. Okay, so let's go ahead and deal with main first. So in this main, we don't have to do much because all we want to do is to call dirty and see what is in register A when it returns. So we still want to kind of initialize the stack pointer, even though it starts with a value of 0 to begin with. It's still a good idea to kind of keep it initialized. And then we just have to call dirty. So we'll do the usual trick, LDIA with .6 plus decrement D stda jmpi to dirty, because that's what we're calling. And this time when it comes back, there's absolutely nothing to clean up because dirty does not require any parameters. So the stack is already balanced by the time dirty returns. All right, so now we're going to specify Johnny. So the reason why this subroutine is called Johnny is because of the movie called Short Circuit. That's it. Short Circuit is the name of the movie, and Johnny is the name of the robot. It's Johnny 5, and hence the name Johnny associated with the value of 5. Yes, it's kind of lame, but but I need to give the subroutine a name other than 5. Alright, so now we have the return code, LD, let's use register C this time, why not? There you go, JMPC. Alright. The next one is Ryan, because Jerry Ryan is the actress of 7 of 9 in Star Trek Voyager. So that's why the subroutine is called Ryan, because we are returning a value of 7, which is the name of the character that the actress played in Star Trek Voyager. And this time we'll use LDB, okay? So there's no restriction of which register other than register A you should use for returning to the caller. Because the whole point of this exercise is don't count on a subroutine not to change a register. And that's part of why I want to kind of use different registers, because to just kind of make that point. Alright, so this is the difficult one, okay? So dirty. And the reason why it's called dirty is because there's a movie called The Dirty Dozen, okay, which is 12. So that's why it's called dirty. All right. So in order to figure out the return value of dirty, we have to call Johnny, and then we also have to call Ryan. Okay, that's pretty easy stuff, right? So we just say LDIA with .6 plus decrement D stda JMPI, and the first one we're going to call is Johnny. And then the second one we need to call is Ryan. Okay, so we're going to just copy these 4 lines, right? Copy, paste over here, change Johnny to Ryan. And now we need to calculate the sum of the return values of those 2 subroutines. So the question is, what are we going to do here? Because at this point, we only have the return value of Ryan. The return value of Johnny is gone. It's overwritten. When we called Ryan, that subroutine overwrote the value of register A already. What are we going to do? Well, register A is important because the return value of Johnny is in register A here. Okay, so right here we have the register A. Register A has the return value of Johnny. And over here, register A has the return value of Ryan. So the problem is there's only one register A. So when Ryan overwrote the value of register A, it overwrote the return value of Johnny. So what are we going to do? Oh, Perry, that's exactly the right answer. Nice, very nice. We have to save it to the stack. Okay, so to save something on the stack is to push it on the stack, right? So what we need to do is to say, okay, I cannot use the value of the return value of Johnny right now because I kind of need the other value before we can add stuff. So we're going to save it on the stack. To save something on the stack is just decrementing the stack pointer. and then store. If that value that you want to save is already in the register, all you have to do is to store that register to where the stack pointer is pointing to. So this is how we push the value of I should say this is how we push the return value of Johnny on the stack. So after this, I can mess around with register A all I want, and it's going to be okay because register A the value of register A is already saved on the stack. So right here at this point, I kind of need it back, but I don't want it back in register A. I need it back in one of the other two registers, B or C. So when we pop it, which is an LD instruction, LD B, D. So I'm going to pop it into register B. But don't forget to increment the stack pointer because once we retrieve the value from the stack, we don't want it to be sitting on the stack anymore. So we have to remember to deallocate it from the stack. So the increment D is for that purpose. So at this point, register A has the return value of Ryan, and the register B has the return value of Johnny. So now we got both return values in two different registers, and all it takes is a simple add instruction. And I would use add AB instead of add BA because add AB will also automatically put the sum back into register A, which is what we need in order to specify the return value. So all that is left here is to continue execution at the caller. Basically, it's the return back to the caller part. So that part is pretty easy to do because all we need is to retrieve the return address, in this case, from the stack. So anything other than register A is fine. Register B or C will be okay. Increment D. This is why I said a little bit earlier, it is the callee's responsibility to deallocate the return address from the stack, and that's what this increment D is trying to do. And then we have a JMP instruction back to where register B is pointing to. That's our point of continuation of this program. So any questions about this code at this point? This is a very simple program to illustrate an important point of, you only have one register A. So if you know that you need the value back from a certain register, you can use the stack to save it. So Perry is 100% correct about the suggestion of using the stack to save the value of a register that can come in handy later on. All right. We got one question and we still got 10 minutes. Wow. Okay. All right. So to reiterate, to add AB, A has the return value of Ryan, and then B has the return value of Johnny from retrieved from the stack. Yes. You said after you add AB, the sum will go into register A. Yes. So that has to do with what column C is documenting the opcode, because it would say, x equals x plus y, x being the first operand. Yep. So as a suggestion for the final exam, understanding the opcode table and being familiar with it is going to help, because then you don't have to use the time during the exam to ask yourself, okay, after an add, which register ends up with the sum? So if you're already familiar with those instructions, the effect of each instruction, that will save you kind of a lot of time during the exam, so you can focus on other things. All right. So Ivan is still typing. I'm gonna wait a little bit here. I'm gonna get out of the editor and just get ready to test run it. All right. Would you copy value of register A to a different register without the stack? That would not be a good idea, because when you call another subroutine, there's no telling what register the other subroutine can modify. In other words, the whole point is, right here, a callee has no obligation to preserve any of the three registers, A, B, or C. Yep. So do not make that assumption. And if you cannot make that assumption, that means you cannot save the value of one register into another register and then call a subroutine and then expect that value to be in whatever register you copy it to. So yeah, there you go. Alrighty. So looks like we don't have any questions, and it's time to test run the code. So this is going to overwrite the original, the other program that I went through, which is the ungraded assignment. And now we can go take a look at the result and see if we have it done correctly. Alright, so the quick way to check is to go to the end and see if register D ends with the value of 0 first. And that it did. Okay, very good. And then the other thing we want to check is to see if register A ends up with a value of 12, because that's the result of calling dirty. So that also happened. So I'm fairly confident that the program is implemented correctly because of what I observed here. Okay, D is 0, 0, A is 0C, and we end up on location at location 28. And location 28 should correspond to the address of the halt instruction. So you can check that by going to the assemble tab. There's a reason why I put analysis right next to assemble, because these two combined is very helpful. So if I go all the way to the end and look at the halt instruction, it is indeed at location 28. So the program did work correctly. Any questions about this one? Now in my Joplin, there was a third program that I wanted to illustrate, but it turned out to be unnecessary. Okay, this one turned out to be unnecessary because the point that I was trying to make using the third program, which is the double plus 3, was already illustrated using the second program, which is this program over here, which is basically saying, you have to save the value of something on the stack. And it is also partially illustrated by the first program, which is to illustrate when you are pushing more than one arguments on the stack, and the latter one, or the one that you push later, if it has to refer to local variables or parameters, the offset to that local variable or parameter is off already, because now we have more items on the stack. So you need to remember to offset whatever is defined in the label by the number of bytes, the number of additional bytes on the stack. So both of the concepts are already illustrated, so that makes the third sample program really kind of unnecessary, because it's a combination of the other two. So now would be a good time to give you guys the access code to the lab today. I usually teach this class as an evening class, so it's just a habit to say, oh, okay, tonight. Nope, no, just today. Alright, so this is the easy one. This one only has, I think, 3 or 4 questions. I cannot remember the number. But it's pretty easy. It's due at 1:20 p.m. today. I think most people are going to be done with it in, at the most, maybe half an hour. Okay, the access code is FIB. FIB. I'm going to put it into the text channel, which is the abbreviated form of Fibonacci. Okay, so this is the program that you need to implement in assembly code. And if you go to the questions, it does have the source code in C right here. So the source code of Fibonacci is right here. Let me kind of magnify a little bit here. So you look at this and go like, whoa, that is cryptic, because instead of the usual way of using a conditional statement, it is using a ternary expression. But we use ternary expression a lot in this class already. So the question is, how do you sequence the things that you need to do in this case, right? Well, with a ternary expression, the first thing you need to do is to determine which branch do we need. And to determine that, you have to evaluate the first part of the ternary expression. If it is true, then you want to return, this becomes the value of the expression. If this is false, then this becomes the value of the ternary expression. Okay, so we need to do this first, right? And then we might go to this one, which is easy, okay? Or there's a rare occasion that we might, well, actually not a rare occasion. Most of the time we want to go for this one here. So when we need to do something like this, what are we supposed to do? Well, it's a combination of things that we have already learned. In other words, I have introduced the pieces already. So the question is, how are you going to put all the pieces together? So we can see that there are two function calls, and we are adding the return values of the two function calls. Wait, that's exactly what you did today, Tack. That's what Dirty is trying to illustrate. Yes, indeed. And each one needs to refer to the parameter, right? So you can see how the first call refers to n, and except it's, we need to pass the value of n minus 1 and not n itself. And then the second one also needs to access n, but this time we need n minus 2. Okay, but if we are pushing the return value of the first call on the stack, doesn't that make, the offset to n off by 1, for the second call? Exactly, that's what the first sample program was trying to illustrate in today's lecture. So all the pieces are already in place. Okay, so I have given you all the pieces already to get this done. What you need to do is to break down the sample programs. Okay, understand the underlying concepts and then reapply those concepts in order to implement this program. That is that's kind of what you need to do. So the main program here is having a just question mark question mark question mark here means you kind of need to determine what value you want to use to test your subroutine. I would suggest passing 0 first, and 1, and then a 2, and then maybe a 3. Okay, in that order. Okay, so don't try to implement this entire code all at once. You might want to just at first, you might want to just replace this part here with a constant. Okay, just replace it with, I don't know, 42, so that you can at least make sure that your ternary expression is working. So once you can confirm that your ternary expression itself is working, then work on the recursive part. Okay, and then the recursive part, you can also work with just one recursive call first before you add the second recursive call. Because if you just have one single recursive call and it's working correctly, that means the way you're calling the subroutine, the way you're passing the argument is indeed correct. That will give you a much better chance of getting the second call also correct. So I would do it in steps. Now the main is not given to you. Well, we are running out of time, but I can give you a main if you need to. That would do exactly what this code is trying to do. So so when you guys are working on the lab, I will give you the TTP ASM code for main, because that's going to be pretty easy. Okay, but this part here, the code is not long. I don't really like to give people long code to write, tedious stuff to do, but it is nonetheless, it can be challenging. And the whole point of this assignment is to make sure that you understand all the underlying concepts. Okay, and the sample programs are here to help you understand the concepts. Did I get the time wrong? That's entirely possible too. Yeah, I think I got the assignment time wrong. Okay, I'll fix that. Thank you, Terrence, for double checking. All right, so yeah, so you guys can get started now. Let's see, recursive call. Yep, it should be December 7th, not the 6th. So let me fix that. Thank you. There we go. All right. All right. So don't put it off, okay? Because this is, if you're already understanding all the concepts, it is still possible that you can make some careless mistakes in your code, and debugging programs like this, can be difficult, and you might want to use the trace analyzer to help you debug a program. And as I said, do it in phases. In other words, make sure that you're pushing the right things on the stack, in the subroutine first, and make sure that you can access the parameter. Implement the ternary expression, with a constant for the third part. If that works, go ahead and do one recursive call instead of two recursive calls. Now, the expected return value with only one recursive call, you can just copy and paste the program in C and C++ into a C++ compiler and let it run, because your program should end up with exactly the same value. The logic of the program should not change depending on whether it is in C++ or in TTP-ASM. So you can also use a C compiler to help you understand what the program is supposed to do, or what value it is supposed to return. And someone may be saying, but recursive call is something new. We have never talked about recursive calls. Is that right? So my question is, how is it different from any normal non-recursive call? There's no difference. Whether you're calling a subroutine from itself or from outside of itself makes no difference in terms of how we perform the call. So that is why a recursive call homework assignment is very important, because if someone claims I understand what is subroutine call but cannot understand how a recursive call is done, that person really does not understand how function calls are done. So that is why we have this homework assignment. All right, so it doesn't look like there are any additional questions. And as a result, I can get out of the voice channel, but I'll still be online to answer questions related to this class. So go ahead and ask in the text channel if you do have questions.